This is the second video on linear transformations. And so we're going to continue to look at some linear transformations. First, let's recall some things that we did so far. And we're going to need these things in our current video. To recall number one, if T is a linear transformation from V to W, this is 1-to-1. And remember, that's the same thing as injective. If and only if the nullity of T, or sometimes called, excuse me, I should say the null set of T, I should say here, the null set of T is 0. So a linear transformation is 1-to-1, injective if and only if the null set is 0, and the null set is 0 if and only if the nullity is 0, which, remember, that means the dimension of the null space of T is 0. So if you end up with a dimension of null space of 0, then that means the only thing in your null space is the 0 vector. And recall, we also have this formula. The dimension of V is equal to the dimension of the null space of T, something called the nullity of T, plus the dimension of the range of T. We had that before. And then we also had, if V is finite dimensional, and U is a subspace of V, and the dimension of U equals the dimension of V, then U is equal to V. So if you have a subspace and the dimension of your subspace is the same as the original space, then your subspace is equal to your whole space. And so keep these in mind. These are things we did previously, and we'll need them in this video. And so let's talk about invertible linear transformations. A linear transformation remember, linear transformation is the same as a linear map from V to W is invertible if there exists a linear transformation going the other direction from W to V such that if you do T then S, you get the identity. And if you do S then T, you get the identity. And so if this happens to be true, then S is called the inverse of T. And T is called the inverse of S. And now we have a theorem. Suppose S and S star are both inverses of the linear transformation T, then S is equal to S star. In other words, there can be only one inverse. So let's go ahead and prove this. Of course, since S and S star are inverses of T, then we have, ST is equal to identity, TS is equal to identity, and also for the other inverse, S star, T equal to identity, and T S star is equal to identity. So keep that in mind. And so let's start with, so now, start with S. And then, of course, that's going to be, you can make that equal to SI, just the identity times S. But of course, from what we have up here, of course, the identity is equal to TS star. And we can reassociate these, make this TS, just using the associativity of the maps. But now this right here, ST, that's going to be equal to I. Then that's equal to S star. So notice we went through these substitutions and we have S is equal to all these, and that's eventually equal to S star. Therefore, S is equal to S star. So there's only one inverse for linear transformation. Another way to say that is the inverse is unique. And there's another important theorem that we have. And this theorem says a linear transformation is invertible that is, has an inverse, i.e., if and only if it is 1-to-1. And remember, that's same thing as injective. And onto. And I'll go ahead and prove this only the one direction. I'll assume of course, let T be a linear transformation. And again, I'll start with the first direction. Suppose T is invertible. And I'll sort of be following the proof of in Axler. Here's a good proof of this. So let W be a vector in space W. Then since T is invertible, we have something like this. So over here, let's say you have your subspace W. Over here you have V. And you have picked something in W. But now since T is invertible, that it has an inverse, that means we can go the other direction. So we can take something from W, anything really that we have in the space W, and use the inverse to take it back to something in V. And let's call that V and V. So we pick something in W, and then it's going to be something in V that it can map back to by inverse. So now, let's say then we can say that TV is equal to T. And of course, when we have over here, we know that T inverse W is going to give us V, so we can substitute that for V. And of course, we can reassociate these. This is going to be I. And that gives us W. So we see what we did. We picked just any arbitrary vector in W and then showed that you can produce it by finding something in you. There's something in V that will produce that. Because so we took this back to here to the V that it would map to in the inverse, then take this and go along and you get that W. So what does that imply? Since we picked just an arbitrary W, we can now say, so for any W in the space W, there exists a V in the space V such that T V is equal to W. Therefore, T is onto or surjective. Now, so that proves part of it, that it's onto. Now we have to prove that it's one-to-one. So once again, suppose T is invertible. And suppose U and V are in the space V such that T U equals TV. Then, since T is invertible, there exists a T inverse. And then we can apply it to this up here. T inverse TU, T inverse TV. So this is going to give us IU, IV, and this is going to give us UV. So we were assumed that there were two vectors that when you apply the linear transformation to them, you get the same value. And then we used the fact that T is invertible and showed that those vectors have to be the same. So T is one-to-one. And of course, what is that? Injective. Now we come to a definition. Two vector spaces are called isomorphic if there is an invertible linear transformation from one vector space to the other. So that's the definition of isomorphic. So two vector spaces are isomorphic if you can find the linear transformation. If there is linear transformation that's invertible between one and the other. And here's now a theorem. This is seems to be a fairly far-reaching theorem. Two finite dimensional vector spaces are isomorphic. Once again, from what we just said, that means that there's a invertible linear transformation between the two of them. If and only if they have the same dimension. Again, you can see why it's so far-reaching. It just says any two finite dimensional vector spaces are isomorphic if they have the same dimension. So that's very interesting. And so let's actually look at this. Once again, I think for these, I'm fairly closely following Axler for these proofs. Assume V and W are isomorphic. And they're finite dimensional. So by definition of isomorphic, there exists an invertible linear transformation T, say from V and the W. So now, since T is invertible, T is 1-to-1. And remember that by previous theorem. we said if it's invertible, it's 1-to-1 and onto. So if it's if it's invertible, we know it's 1-to-1. And so, and also from what we had last video, then the null space of T consists just of the zero vector. So, and also because it's invertible, T is onto W. So let's see what we have. So first we're assuming we have isomorphic vector spaces. And by definition, that means we have an invertible inner transformation. And from the previous theorem, since T is invertible, it's 1-to-1 and onto. And then since it's onto, we know that the null space is 0. And then, so since T is onto, then the range of T is going to be all of W because it's onto. So now we can use that equation we reviewed at the beginning, which says the dimension of V equals the dimension of the null space of T plus the dimension of the range of T, and then dimension of V. And then remember, since the null space just has a zero vector, the dimension null space is 0 plus the range, the dimension of range of T. But we just said that the range of T was equal to W. So that means we can replace the dimension of the range is T with the dimension of W. And so then dimension of V is equal to the dimension of W. So that's going in the one direction. Now let's go in the other direction. When this way, assume that V and W are finite dimensional. And have the same dimension. Let V1, V2, Vn be a basis for V, and W1, W2, Wn be a basis for W. Again, since these are finite dimensional vector spaces. They each have basis. And since they have the same dimension, they're going to have the same number of basis vectors. And so now let T be a linear transformation and let's assume T goes from V to W, defined by T takes the first basis vector V and maps it to the first basis vector W. The second basis vector V, the second basis vector W, all the way through for all the basis vectors. So we're defining our linear transformation just to have these particular properties, and that those would be easy to define the linear transformation that way. Then if you take, say, a linear combination of the vector of the basis vectors of V, and to take a linear combination, so we have these constants A1, A2, etc. And now we can actually break these down. Remember, because T is a linear transformation, we can decompose these this way. Again, because T is linear. And now what do we have? We have A1, W1, A2, W2, AN, WN. Because that's the way we defined our linear transformation to give us that. So now, notice since, again, these W's are the basis vectors, since these basis vectors span W, span the space W, we can get any W in W by changing those constants. Right, because that's the definition of a basis. Remember, a basis spans the space, and the basis vectors are linearly independent. So right now we just know that they span, so it means we can always find these A's will produce anything in there. And so of course, that what that furthermore means, those A's apply over here as well. That means we change these A's to get whatever we want in W to get any vector in W. That also means our transformation was able to produce those because we're changing those same A's, giving them the same value here. So that means we can produce any W by changing these A's here, which means we can change the A's here and always put something in here that will produce that W. So that implies T is onto or surjective. Now, since the W's, W1, W2, Wn are linearly independent, then for each W, there is only one set of the A1, A2, AN that will produce that W. Again, because they're linearly independent, there's only one set will the produced set of A's will produce that W. So then that means same thing that you're putting your T values in, they're using the same A's to put your A1, V1, A2, V2 in the T. And so there's only one way of doing that. So only one A1, V1, A2, V2, A and VN that will produce each W. Therefore, T is 1-to-1. Or injected. So we've shown T is 1-to-1. And onto. And therefore, by previous theorem, T is invertible. And remember that part of the proof, we started out by assuming that U and V were finite dimensional and have the same dimensions. And we ended up proving that there was a T, a linear transformation from V to W that was 1-to-1 and onto. And then we could then show that that means that T is invertible. And so that proves the second part of the theorem, that if, therefore, V W are by definition isomorphic. And now let's do one more theorem. Suppose V is finite dimensional. If T is a linear transformation on V, what does that mean? I.e., T is a transformation from V to itself. So now we're talking about linear transformation of that takes vectors from V to V. Before we we're taking, doing linear transformation, taking vectors from one vector space to another, but this is taking them to the vectors from V to V. Then the following are equivalent. A T is invertible. T is injective. T is surjective. Again, remember, injective means one-to-one. Surjective means onto. So we're going to see if we can prove this. Move this up a little bit here. It's a proof. So again, we're assuming T is a linear transformation from V to itself. Now, we already know something. So now mainly what we have to show here, is that if T is invertible, then it's injective. If something's injective, then it's surjective. If it's surjective, it's injective. If it's surjective, it's invertible. We have to show these all go both, all these combinations go in both directions. So now we know some things already. We already know some of this. So we know if T is invertible, . we know that it's injective, or 1-to-1. So we can go in this direction. And we know if it's invertible, it's surjective, going this direction. So we know those so far. Now we don't know that this implies this, or that this implies this. And we also can't say that injective implies invertible. We can't say surjective implies invertible. Now we do know from our previous theorem that if we have both injective and surjective, then it's invertible. But we can't say for just one of these. Now again, we're dealing with just a linear transformation to itself, from a linear transformation from the vector space to itself. So we are going to try to prove these other missing arrows here. So let's go with that. So once again, we're assuming it's a linear transformation. Now, suppose T is 1-to-1. By a previous theorem, this implies that the null space of T is just a zero vector. And then also, from what we said at the beginning of the video today, so that means the dimension of the null space has got to be 0. Now we're going to use that equation that we had. Dimension of V is equal to the dimension of the null space is T plus the dimension of the range of T. So let's work with this. Dimension of V. Now we said dimension in null space was 0. The dimension of the range of T gives us that. Now, so therefore, the dimension of V is going to be the dimension of the range of T. Now, of course, the range of T has to be a subspace. And also, since the dimension of V equals the dimension of the range of T, then, like I said, since this has to be a subspace, and so you remember from before, if we have the dimension of a subspace of equal to the dimension of the space itself, that means that the spaces have to be equal. So then T is onto surjective. So now we have part of this. So we here, remember, we assumed that T was injective, and we now showed that this automatically proves that it's going to be surjective. So how about going the other direction now? Suppose T is onto surjective. This implies that the range of T equals the dimension of V. And of course, then this means that the dimension of the range of T equals the, excuse me, the over here, I should have just said V up here, excuse me. Please fix this. We're assuming T is onto, and then this implies that the range of T is equal to V, just equal to V. Now, then we could say, of course, since the range of T is equal to V, that means the dimensions of each of those have to be the same. And once again, use our equation. Dimension of T, which is null space. That pencil's falling apart here. T the range of T. Just use that same equation we've been using. And now these two, the dimension of V is equal to the range of T. So these can cancel. So the dimension of the null of T is 0. And that implies, therefore, the null of T is just a 0 vector. So you remember from a previous theorem, so T is 1-to-1. So now we've filled in all the spaces now. So notice what we've done. We've assumed that T was 1-to-1, and we proved it was onto. So we proved this. Let me fill these in a little bit here. So we started out with just having so we start out with this. Now we showed that if something's injective, then it's surjective. And now here we showed something was surjective. We showed now that it's injective. And so now what does this mean? Since injective implies surjective and surjective implies injective, that means that if we have just surjective, we have both of these. If we have just injective, we have both of these. And remember from a previous theorem, that meant that if you have something is surjective and injective, then it's invertible. Now, so once again, since if T is injective, then it's surjective. If it's surjective, then injective. So if you have one, you have both, which means it's going to be invertible. Therefore, if T is surjective or injective, it is invertible. Now, something very important here is this only applies if you have a linear transformation from V to itself. We don't have that if you go from V to another space. You don't have all of these connections because remember one place in the proof here said, remember over here, we have that the dimension of V was equal to the dimension of the range of T. And then we could say that this implied this, but we were only able to do that because we knew that this was a subspace of V, because we're mapping from V into V. So we couldn't, under normal circumstances, do this. So you could even put in that space right there. Then since range of T is a subspace, and let me just put maybe a subset of V, then we can say V was given this range. So that's what allowed us to do that, is because we're just mapping from V to itself. In any case, that's a very important theorem, that if you do have a finite dimensional vector space and you're mapping, doing a linear map from the space to itself, if you have any one of these, you have the other two.